In this section, we're dealing with derivative as a function, and there will be times where we are asked to graph the derivative if we are given the original function. And there's 3 steps that we got to follow in order to do that. First thing we got to do is we got to find the places where the value of the derivative is 0. That means the slope, because derivative and slope mean the same thing, the slope of the function is equal to 0. Okay, so we got to find where that happens. We got to identify the intervals, these places in between these zeros that we just found. Intervals where the value of the derivative, same thing, synonym for that is slope of the function, is either positive or negative. And then we're going to use that information and we're going to graph the function, the derivative. So here's f of x, and we're going to graph f prime of x. So the first job is to figure out where's the slope of this guy 0. Where is the slope of f of x 0? Well, it appears to happen right here. So the value of the derivative at that x value has to be 0. It looks like the slope is 0 right about here-ish. So at that x value, I want to have the value of the derivative be 0. Same thing happening here. The value of the derivative has to be 0. And now that I've identified my zeros, I've got a bunch of intervals. I got before we ever get to this 0, I got in between these 2 zeros, and I got in between these 2 zeros, and I got what's going on after this 0. Now it appears as if all of these slopes, therefore the value of the derivative, leading up to this first 0, all of these slopes are negative. So I'm going to make sure that I have negative values for the derivative in that interval. In between these zeros, looks like the slope is always positive. Got to make sure my derivative has positive values there. In between these zeros, it appears as if all of these slopes are 0. I'm sorry, all of these slopes are negative. And then after that 0, it looks like all of the slopes, and therefore the value of the derivative is going to have to be positive. So now to draw the derivative, all I'm going to do is make sure that I have negative values, that I get to 0, that I have positive values in this interval, but get back to 0 in time, then have negative values before you return to 0, after which you have positive values. A little bit of practice, and that's a pretty easy skill to master. Now, derivative can be written as a function of x. We've seen this exact same thing in definition of derivative. We've seen this. But instead of x's, we've had a's. And all that a stood for was some x value. Well, now we're going to have x's in place of x values. Right? So let's find the derivative. And the derivative is going to be a function that's got x's in it, because we're not finding it at any particular point. So we're going to take the limit as h approaches 0. And we're going to put x plus h in place of these x's. We're going to have x plus h, which needs to be squared, minus, we got to put an x plus h in there. And then we're supposed to subtract f of x. Well, I got to subtract f of x, which is x squared minus x. And then I got to divide that by h. Okay? So we're going to have the limit as h approaches 0. And I'm going to have x plus h squared. So that's x squared plus 2xh plus h squared. Then I got to subtract the x. I also have to subtract that h. You got to subtract both of those terms. Then I'm going to be subtracting x squared, but I'm going to be adding the x because I'm going to be subtracting negative x. And then make sure that you remember to divide by h. All right. So that's kind of a pain. That's a lot of terms. But I think we notice that this x squared and this x squared, gone. We got negative x plus x, gone. And it's not unusual to see this entire thing, this f of x is going to go away. It should happen every single time. If it doesn't, you've made a mistake. And now everything that's left has got an h in it. So if I'm taking the limit as h approaches 0, I got to take this term and divide it by h. And that's going to be 2x. Plus, I got to take this term and divide it by h. Minus, I got to take this term divided by h. So that's going to be minus 1. And if I actually take the limit as h approaches 0, I'm going to put a 0 in place of that h, and I think I'm just going to get 2x minus 1. Don't lose track of that. We're going to use this later on. We've just found the derivative of x squared minus x. And this is that derivative. We're going to use that later on. Okay, what about this next guy? If f of x is that, let's see, now I got to take the limit as h approaches 0. And I've got to get a function for my derivative. So I can find the slope at any x value. I need f of x plus h, which just means I'm going to put that underneath the square root sign. Then I got to subtract f of x. And I got to divide the result by h. Wow, what do you do with this? That last one, it was nice, and things just went away, and nothing's going away here. But if I put a 0 in place of the h, I am going to get 0 on top, 0 on the bottom. How do you handle 0 over 0? Well, one of the tools we had back in Chapter 1 for handling 0 over 0 in a limit, which is exactly what we've got here, is conjugate. Square root of x plus h plus the square root of x. And on the bottom, square root of x plus h plus the square root of x. Okay. Well, if I multiply this out and do it correctly, I'm going to have the limit as h approaches 0. It's very important to multiply out the numerator. This times this is x plus h. Now, the reason you multiply by the conjugate is because this term and this term, the o and the I of FOIL, are opposites of each other, and 100% of the time are going to result in 0 when you multiply by the conjugate. And so now I need to do L of FOIL. And the opposite of the square root of x times the square root of x will be subtracting an x. And on the bottom we've got an h. And then we've got this square root of x plus h plus the square root of x when we multiply these guys up. Now you'll notice that the x's go away. You'll notice that you're left with an h on top, and the h on top divided by the h on the bottom result in, well, h divided by h is 1. You've got a 1 on top. So if h is approaching 0, if this h, the only remaining h, approaches 0, you now are left with a 1 on the top. And then on the bottom, you've got a square root of x plus another 1. You've got 2 square roots of x. And in calculus, not important to rationalize the denominator. You can leave a square root down there. So the derivative of this function, the slope at any x value for this function, is found by putting those x values in here. What's the slope of this function right here when x is 4? Well, 1 over 2 square roots of 4. It would be 1/4. You can find the slope of this function at any x value. Now, differentiation, term that we'll run into. Differentiation is just the process of calculating the derivative. And there's a lot of derivative notation that we find on page 117, and I've copied that here. This means the derivative of f of x. This means the derivative of some y equals equation. This means the derivative of whatever y function was with respect to the variable x. We don't see this one very much. This means take the derivative with respect to x of this function. And these are guys that we really don't see very much. But we will see these 4, meaning find the derivative. Now, where is this function differentiable? Where can you find the derivative? Something's differentiable if you can find the derivative. A little clue on any time you see an absolute value function all year long and you're asked to answer questions about an absolute value function, I cannot think of one single time where the key to answering an absolute value question wasn't draw the graph. So I'm always going to try and draw the graph of the absolute value function so I can answer the question intelligently. Now, absolute value, I think you realize this, looks like that. Can you find the derivative here? Well, sure, that's got a definite slope to it, and I think you'd realize that the slope is -1. And I think over here you can find the slope of this guy. I think the slope of that guy is always 1. But what's the slope right here? What is the slope where this -1 meets the +1? And that is a place you cannot find the derivative. It's not 0. This thing doesn't ever level off and have a level part to it. And it's not -1 and it's not 1 because it's transitioning from one to the other. So where is this differentiable? I think from -infinity all the way up to 0. But let's not include 0 because we can't find the derivative there. And then starting just the other side of 0 and going all the way to infinity, we know the derivative is 1. So this, or these, are the intervals where that absolute function, absolute value function, is differentiable. Now, a function is differentiable if you can find the derivative. And as we've just said, if we look at page 120, figure 7, this is figure 7 from 120, where are we not differentiable? Well, we're not differentiable whenever we have a corner. And you need to know that anytime you see a corner, you're not differentiable, and that is the reason we're not differentiable. Section 1.8, we talked about continuity. Well, here we got a function that's not continuous. We don't know how to find the derivative at the x value of a. There's no way we can assign a numerical slope to that thing. And the same thing goes if you got a vertical tangent. Okay, right here, that point. The vertical tangent means the slope is so big we call the slope infinity, and so we can't assign a numerical value to it. Now, question. Now, here's a theorem. Theorem is a provable statement. If a function is differentiable at a point, then it is continuous at that point. Is the converse true? And the converse means just switch the if and the then around. If a function is continuous at a point, is it differentiable? If a function is continuous, then it is differentiable. Is that true? Is this function continuous at a? Yep. Is it differentiable at a? Nope. This function is continuous at a, but not differentiable at a. And so therefore, although this theorem is true, is the converse true? Is the switched around statement true? No, it isn't. All right, final slide. I think it's the final slide. This is not the final slide. Dog. Okay, find the second derivative. Now that's the notation for second derivative. If f of x is equal to this. We've seen this before. And the second derivative is the derivative of the derivative, and we know what the derivative is. We found this today. Said we'd come back to it, and we're back to it. So now let's find the derivative of that. Let's take the limit as h approaches 0 of f of x plus h, or in this case f prime of x plus h. And if you put an x plus h in here, you would get 2 x's plus 2 h's, wouldn't you? Minus 1. And then we got to subtract this thing. And then we're going to divide by h. So we're taking the derivative of the derivative. We're treating this guy as if it was the function and finding its derivative. Well, the 2x's, poof, poof, gone. Minus 1 minus negative 1. No surprise, when you take the derivative, that thing's going to be gone. And we're going to take the limit as h approaches 0 of 2h divided by h, which is just 2. And since there isn't anything to put a 0 in for, this limit just has a value of 2. The second derivative of this function is 2 everywhere. The slope of the derivative is 2 everywhere. Well, that's not a surprise. What's the slope of this line? 2. The derivative of position, we've already said, is velocity. What do you suppose the second derivative of position is, or the derivative of velocity? The slope of velocity gives us acceleration. And you're going to see lots of questions this year about position and velocity and acceleration and the relationships between those three things. Finally, table gives the number of MFHS seniors who said they smoked during various years between 2010 and 2016. What is the meaning of the derivative in 2014? What is the meaning of that? Anytime you ask for the meaning of the derivative, the meaning of the slope, it is always the rate. Oh, got excited. It is always the rate. Derivatives are always rates. The rate at which blank changes with respect to blank. And in this case, we're looking for this rate in 2014. Now, this first blank is always a description of the Y value or the output value with respect to whatever the X or the input or the independent variable. So we're going to fill in the blanks. This is the rate at which the number of smokers changes with respect to, well, T stands for time measured in years. The rate at which the number of smokers is changing with respect to time in years in the year 2014. Now let's estimate. Let's estimate what that derivative is in 2014. Well, I've got a table, and to find the derivative, to find the rate at which things are changing in 2014 from a table, you take the points closest to it, and you find the slope between them. And so we're going to have to take y2 minus y1 over x2, whoa, got excited, over minus x1. So I'm going to have 22 minus 26, or negative 4, over 2015 minus 2013, 2. Now I've got to have units. And the units down here, this represented negative 4 smokers. And 2015 minus 2013 was 2 years. And if I simplify this fraction, I get negative 2 smokers per year. We're losing 2 smokers per year in 2014. That's our estimate. Now, construct a table. Okay, we're not going to do it. I know this was negative 2. Whoopsie. I know this was, oh, it's doing it again. I know this is negative 2. Could I find it for 2013? Could I find 2013? Could I find y2 minus y1, x2 minus x1? I could do that. I think you have the idea from here. And so this is how we're going to come up with the derivative as a function.